Hello, anatomy and physiology. Um, this feels familiar to me from teaching last year. Anyways, I am here from home. I'm sure you know I've been sick. Um, I don't know if it's COVID. I've been waiting on a test, so we'll see. But I'm feeling well enough to come to you guys this morning and give you your notes for today. I'm going to hold off on a few of the other activities I would like to do if we were back in class. You'd be doing a acid and base lab and a buffer lab, and I hope we can do that as soon as I'm back and as soon as we're all back in school. And she won't sit here the whole time, I don't think, but I want to introduce you to Penny, one of 3 dogs. Although she looks like a cute little puppy, she's the oldest one. She just got her puppy cut haircut. But she always likes being on my videos, so I thought I'd let her participate today. I actually don't have my study guide sitting in front of me, but I believe this is somewhere around page maybe 8 or 9 in your notes packet. But find the section that says properties of water, and you're going to fill this out along with me as we go through the notes here. So ideally, we would have already talked about acids and bases, but that's okay. It's not necessary for this unit here. But one thing that's really important for the human body is water. We know it's one of our essential nutrients. And the reason why water is so important is it has these really unique properties that we're going to go through. So the first is that it has a high heat capacity. What that means is that it doesn't heat up easily and it doesn't cool down easily either. So it will take a whole lot of energy to boil a pot of water. If you've ever added butter or oil to a hot skillet, it sizzles almost instantly. But if you are trying to boil or get water to sizzle, it takes a long time. And because of its polar bonds, those molecules stick together and they don't break apart very easily, much like other substances are able to. Water is polar, as I've already mentioned, and as we've gone over, I think you went over that with your sub in the notes. To be a polar molecule, it means that it's covalently bonded to each other, but it doesn't share the electrons equally. And because of that unequal sharing, it ends up having 2 dipoles or electronegativities to it, and it will stick to other polar molecules. So it forms hydrogen bonds, and that's kind of the stickiness that it has between water. And so because of its polar bonds and because of hydrogen bonds, this is why ice floats in water. When ice freezes, most things get smaller when they freeze. Ice is unique in that it expands because that hydrogen bond pushes those molecules apart from each other. It also creates surface tension. If you've ever belly flopped from a high building, you have felt that surface tension, or if you've ever seen those little water bugs skitter across the water surface, that's because of surface tension. It also is sticky, meaning it sticks to each other because of those hydrogen bonds. Now, because it's polar and because of those 2 charges, it ends up being an excellent solvent. And a solvent is something that dissolves other things, right? And so it pretty much dissolves anything at all that has a charge, NaCl, sodium, chloride, salt. Those 2 charged molecules very easily break apart in water in order to dissolve. It also is actually very chemically reactive. I've mentioned this already before when we talked about the importance of water, but it is really important because it will be involved in almost all the chemical reactions we're going to discuss later. Dehydration synthesis, a fancy word, but hopefully you heard it in Bio 1-2. This is when I want to take 2 molecules and hook them together, in this case, probably biomolecules like an amino acid and amino acid to build a protein. In order to hook them together, I need to remove a hydrogen from one and a hydroxide, an OH from another. And when I remove one H, an H and an O, these two molecules can hook together. Well, that was two H's and an O, or H2O. So dehydration synthesis means you remove a water molecule in order to hook two things together, to synthesize them and create something new. The opposite is also true that water does, is hydrolysis. It can break apart molecules by simply adding water. So the same is true if you want to break down a protein. Your body adds water with the assistance of an enzyme, and it adds a hydrogen to one molecule and an OH to another, and you break those two molecules apart. We'll hopefully be able to demonstrate that in class later. Cushioning is the last one. Our body has tons of water in it, and we find our high water areas and other protective measures in our body, in particular in our nervous system. We have something called cerebrospinal fluid, and it's mostly water with other important things inside of there for our nervous system. But what this water does is it surrounds your spinal cord. It also surrounds your brain, and it's a buffer between those sensitive nervous tissues and the bone, so your skull or your vertebrae. And it acts as a little like cushioning or airbag. If you're in your car and you're wearing your seatbelt, because I know you do because you're safe students, and you slam on the brakes, your seatbelt is going to prevent your body from lurching through your car windshield. However, objects in motion tend to stay in motion. Your seatbelt stops your body, but your brain is actually in some liquid as well. And so your brain keeps moving forward inside of your skull, and it can actually crash into the front of your skull bone, your frontal bone, and cause some damage to your brain if it weren't for cerebrospinal fluid. Cerebrospinal fluid basically acts like a little airbag inside of your skull that prevents your brain from getting jostled around inside your cranium. Cool stuff. You might not think so, but water is very important. All right. I knew that was going to go fast. You'll answer some questions about water for your homework assignment. So I wanted to introduce to you our major macromolecules. We're going to spend a lot of time on these before we take your test, which I haven't given you a date yet. Things are weird. I've been gone, so I'm probably going to give us more time on this unit than I normally would. But we're talking chemistry, right? Okay. The first two things that you'll see here is we've got inorganic and organic listed here. Because this is anatomy and a biological science, we're mostly concerned with our organic chemistry. And what does it mean if something's organic? That's not the same as the health food store. Okay? That just means it is not made with man-made pesticides. Organic, biologically, the definition is very simple. It just means that it contains carbon. Most people just say it contains carbon, which is not entirely wrong, but it also must contain hydrogen as well. And we'll see why when we look at the definition for inorganic. But pretty much anything that has carbon in it, for the most part, is organic, meaning coming from or relating to or a part of living things. Now, my diamond ring, which I super duper love, let's all look at it, is pure carbon. Okay, just like coal is pure carbon. It's not living, it's not organic. So that's why we add this little and hydrogen piece to it, because it all has to do with how carbon and hydrogen are in a relationship kind of with each other. We'll get more into that later, not today though. Inorganic is basically molecules that don't contain carbon, with the exception of carbon dioxide. That is not a living molecule, even though it's in us. It's important for us. It's a waste product we produce, but it is not considered a living organic material. So notice no H in CO2. And so again, it doesn't fit the definition of organic. So, but it doesn't contain carbon, it's inorganic. So some examples of inorganic things that we are going to find important for the human body is water, as we've just spoken about, salt. So NaCl, or you with the sub, you should have talked about that very classic ionic bond, NaCl. Very important. It's a salt. It's an electrolyte. Hopefully you guys got to see that demo. Some of you haven't yet, but you will. That's what you'll do Wednesday when you guys come back, and either with me or with a sub. And then we have acids and bases. Acids are defined as proton donors, so hydrogen ion donors. We'll talk more about them later. We have an acid-base lab we'll do. And then bases are hydrogen acceptors, so molecules that pick up loose hydrogen ions floating around. Acids give them off. HCl, hydrochloric acid, a very typical acid we use in chemistry, is an example. HCl is an acid, hydrochloric acid. In water, it disassociates, and that hydrogen strips from that chloride, and becomes a hydrogen donor. And then the last one, which we have a lab that we are going to do on as well, is buffers. And I wanted to wait and tell you more about those later. But buffers are not organic, but they are biologically important. And so we in anatomy care about them. All right, now jumping back over here to our different types of organic molecules. Once we finish covering our buffers and acids and bases, we will spend the rest of the time talking about these 4 things and getting kind of in depth on them. Today's just a little intro to them. So carbohydrates, hopefully you remember some of these from Bio 1-2. Our proteins, carbs are like the sugars, proteins, the meat, the muscle. Also, they literally build almost everything in your body. Lipids, which are sort of the fats, but not just fats, we'll see. And then nucleic acids, which is like the DNA and RNA of your body. All right, so going through each of these in a little bit more detail. Carbohydrates, as I mentioned, are your sugars. And every single one of these are big molecules. They're macromolecules, and they're made up of lots and lots of tiny things put together. Lipids are different, but for the most part, all of them you start hooking small pieces together to form a large molecule. So they all have a starting unit or a subunit, which we're going to call monomers. But you may have called them subunits in Bio 1-2. Hopefully these sound familiar as well. You'll need to know that for your homework assignment tonight. So monosaccharides are our mono 1 saccharide sugar, our single sugars or simple sugars. Glucose and fructose are classic examples. That would be the monomer of carbohydrates. When you take 2 monosaccharides and hook them together through dehydration synthesis, the term I mentioned before, where we remove water to hook them together, we make a 2 sugar or a disaccharide. And then if we end up hooking a big long chain of them together, we end up with many sugars or a polysaccharide. Starch, like what you find in potatoes, is an example. Glycogen that your liver stores is another good example. But these are large molecules that your body usually stores for glucose uptake later. The only one actually humans store in our bodies, in our livers, in our glycogen. Proteins, they have a monomer, that's the amino acids. And the amino acids, there's 20 different ones. We're going to spend a good amount of time talking about them and their uniqueness. And the way that proteins arrange themselves become pretty unique. When we start hooking a bunch of amino acids together, we call them a polypeptide. And the reason is that the bond that forms between them is called a peptide bond. You may remember protein synthesis from Bio 1-2. This is where you had the ribosome and you had like the messenger RNA coming through, and your ribosome was reading the codons, those 3 letters, and then adding an amino acid every time it could read 3 of them, sort of the building blocks of what DNA does for us. And so when we start hooking that long chain of amino acids together, they form a peptide bond. And so we call a chain of them a polypeptide. And then as it folds and becomes more unique in shape, we just call it a protein. And depending on what it does for you, it's either a functional or a structural protein. And we will get more into those later. Basically, is it support for your body? Is it like keratin in your hair? Or is it an enzyme that's maybe allowing chemical reactions to happen? All right, and then down to our lipids. So lipids are a little bit different in that depending on what kind of lipid we're talking about, their structure is a little bit different. We'll get into that in more detail later, but classic lipids include our fats, the phospholipids that make up your cell membrane, and steroids. Steroids are unique all in themselves. Their structure is very different, but the fats and phospholipids both have a similar structure to them. Some examples of steroids that you've probably heard of are things like cholesterol. Vitamin D is a steroid, and testosterone. So those 3 things are all organic. They're all part of our lipid group, but they have kind of a different form to them. And then lastly, if you noticed, I didn't give you a monomer for this one. We would oftentimes say that the fatty acid is the monomer for lipid. I put an asterisk by it because that's not the case if we're talking about our steroids. And it doesn't act the exact same way that amino acids and monosaccharides do. But that's kind of the best answer we have for that one. And then the nucleic acids, okay, we have nucleotides. Nucleotides is the monomer of that. This is, well, we'll get into that structure later. And our classic examples of nucleic acids are DNA and RNA. That's it for your guys' notes today. You do have a homework assignment that goes over this material. Obviously, we're not in class. You don't have to do this exit ticket, but think about it. Can you list the 4 macromolecules and each monomer that belongs to each one? You're going to do that on your homework assignment. So message me on Remind if you have any questions. You can comment add a private comment in Google Classroom as well. I should be able to get those from you. And I'm sorry you guys are all stuck at home today and not at school. They're doing a deep clean and some contact tracing. So hopefully we'll be back on Wednesday. I hope I'm back soon, hopefully by the end of this week. And I will see you guys in person, I hope, soon. Take care. Bye.